As part of the response to climate change, one of the things that we're doing is learning how to take carbon dioxide, carbon out of various fuels and things like crude oil and natural gas. And a professor at the Simon Fraser University in Burnaby, BC, is leading this charge. His name is Stephen Holdcroft. We're going to talk to him about his research. So welcome to the interview, Stephen.
Well, thank you very much. It's a pleasure to be here and talk a little bit about our research in energy.
Maybe what we could do is just start with an overview of what you and your team are doing.
Yes, certainly. We're involved in inventing and discovering research, new materials that are helping to hopefully clean the planet and make a transition away from the petrochemical industry for fossil fuels, move to a greener energy source. And if CO2 is being emitted from various sources, then we want to take those CO2 sources and convert them into fuels and reuse them.
Now, I've heard of other projects that are trying to do this, and the basic idea is that, as I understand it, is you capture and then sequester the CO2, and then that can then be turned into a biofuel. Have I got that correct?
Yes, it can be converted into a fuel, but it can also be converted in principle into a chemical feedstock that can then go on to used in plastics. And those plastics eventually, if they ever become CO2, then we can recapture the CO2 and then reuse it all over again. So it's like a circular economy.
Oh, no, that's fascinating because that's something I had not heard. Could you elaborate on that a little bit more about just, maybe a little more detail on how that would work?
Yes, so again, if one can capture the CO2, whether it's sequestered in underground and with massive tanks or canyons underneath, that's there as a source, or it may be captured as a flue gas coming from emissions. And so one of the products that can be made from CO2 reduction is ethylene, for instance, which is a primary feedstock for polyethylene, which is of course a plastic that's used all around the world for many different applications. So instead of having to take crude oil and refine it into ethylene, we can potentially get CO2 and convert it into ethylene and then reuse that in the polymerization to make polyethylene and so on.
Now, let's talk about a practical application of that, because in Alberta, there are a couple of carbon capture and sequestering projects. The big one is Shell Canada's Quest project. So if I understand this correctly, your technology that you eventually develop and commercialize would be available to then take that CO2 that's sequestered, process it in some way, and turn it into ethylene, which then, Alberta is the second largest petrochemical cluster in North America, and you could then have a relatively inexpensive, presumably, new feedstock for that industry.
That's the general idea. These are big pictures, of course, and they require a lot of advancements in the technology. And each group, each institute is playing its part. In our particular part, we are focusing on, ironically, the membranes that help the CO2 separate the gases and the products in the CO2 reduction. Some groups are working on the catalysis, some are working on the engineering. And our expertise is that we make the membranes that are stable to allow this process to come together.
That makes you a membrane expert, and I'm very interested in this because we've interviewed a couple of other companies like Summit Nanotech out of Calgary that are using nanotube membranes to do things like take lithium out of salt water in Chile. This is very interesting. Is that similar kind of technology?
It's in a broadest sense, it's similar in that it's using, you're trying to separate reactants and products or species, and that's what we do also. But the applications and the chemistry involved are very different. And so in our instance, CO2 reduction requires quite caustic conditions, alkaline conditions, and membranes that can survive caustic alkaline conditions just didn't exist. And at Simon Fraser, we were fortunate to discover a material that is not only can transport the ions needed for the reduction of CO2, but also is stable to alkaline conditions. And that's where the major discovery coming from basic research came from.
This is interesting. Then, would it be fair to say, Stephen, then that that depending on the application in energy, there might be application for who knows how many of these specific membranes, and that there's an opportunity for Canada to become a leader in membrane research and development and commercialization and manufacture, that sort of thing? Is that opportunity exist?
Oh, absolutely. And that is the plan. In Canada, we have an amazing history of developing electrochemical technologies, and I won't list them, but they're involving water splitting to hydrogen and oxygen, and using hydrogen and oxygen in fuel cells. And in fact, in Canada, we have we have a gap in that technology, in membrane technology, the scale up of it. So 3 years ago, we formed a company which is now spun off and run independently in Vancouver, and they're aiming to be the world leaders in this technology. And it is a massive technology, and we're producing hundreds and hundreds of kilograms of material and thousands of square meters of polymer that will hopefully supply similar CO2 electrolyzers around the world.
If we think of this membrane as a technology that will, move from the lab and eventually into the market and then start to, gain acceptance, what are the one or two key obstacles to adoption of the membrane technology?
There needs to be development and future research into the catalyst that can selectively convert CO2 into carbon monoxide, into methanol, into ethylene. Each catalyst works differently, produces a different product. And then the membranes have to be tailor-made for that particular product and be stable. And then one has to put all this together in an engineering way at scale. And so there are challenges there, from the basic chemistry to physics to chemical engineering and large-scale production. And then the generation of large-scale materials and the production of it, the quality control. So it's a fantastic challenge, and we're all very excited about it.
Last question, and Stephen, you're a professor, you teach at SFU, and I'm sure you get asked this question by your students all the time. Is there opportunity for young Canadians to get educated and trained in the technical requirements for this industry, and are there then employment opportunities to help you and companies like the one you mentioned in their work?
Oh, yes. It's a fantastic time to be in the field, whether you're a polymer chemistry researcher like me, or an electrochemist, or a chemical engineering. This whole field of green energy, clean energy, whichever way you want to call it, is a growing field. The number of jobs are increasing. I don't want to say exponentially, but they're rising on a power scale. And Vancouver's a fantastic place to do this research, but we're not the only place doing it. It's a wonderful opportunity in almost every discipline you can think of.
Stephen, thank you very much for this. I find your research fascinating. Another little insight into how the energy transition, over to this clean energy, as you say, is happening. So thank you very much for this.
You're very welcome. Pleasure to speak with you.